Hey everyone, welcome to The Explainer. So, if you're the kind of learner who absolutely loves taking complex problems and breaking them down into clear, bite-sized pieces, well, you are in the exact right place today. We're going to jump right in and crack a classic organic chemistry puzzle together step by step. We're looking at the reactivity of phenol, and we're going to strip away all the confusion to reveal the really elegant, structured logic underneath it all.
Okay, take a look at this. It might look a little intimidating at first glance, right? We've got this big block of chemical formulas, branching reaction pathways, some foreign text, but I want you to look at this like it's a mystery we're investigating. We've got a primary target, a lineup of chemical suspects, and a strict set of immutable chemical rules to guide us.
Here is our roadmap for the investigation. First, phenol's reaction test. Second, why weak bases fail. Third, the ether experiment. Fourth, the reactive compounds. And finally, the final answer.
All right, let's kick things off with Section 1, phenol's reaction test.
So, what are we actually trying to figure out here? The main question from our source material is actually pretty straightforward. Which of these compounds will successfully react with phenol? In this whole scenario, phenol is our VIP. It's the central molecule we're testing. If you look over on the left, you'll see phenol is acting as the starting point for 4 totally different reaction pathways.
So who's trying to interact with our VIP? Well, the problem gives us 4 distinct chemical candidates. Candidate 1 is RbHCO3, which is rubidium bicarbonate. Candidate 2 is a molecule with the formula C6H5OC2CH3. That's an ether. Candidate 3 is concentrated nitric acid, and candidate 4 is ethanol chloride. Our job is just to walk down each of these paths and see exactly what happens.
Moving right along to Section 2, why weak bases fail.
Okay, so the big question for our first pathway, will rubidium bicarbonate, our candidate A, actually react with phenol? Does this specific compound have the juice to break phenol's bonds and force a chemical change? To answer that, we have to look at comparing acidity. You see, one really simple rule governs this whole interaction. Phenol is significantly less acidic than carbonic acid, or H2CO3. And honestly, that relative difference in acidity, that is absolutely the crucial deciding factor here. Because phenol is weaker than H2CO3, it just simply cannot react with weak bases. Our source explicitly points out that this prevents it from reacting with things like RbNHCO3, NaHCO3, and Na2CO3. Notice that super clear, solid X on the top arrow? That X is chemistry shorthand for no reaction. So candidate A, total failure. Okay, on to Section 3, the ether experiment. Let's pivot and see what happens with our next candidate. What about candidate B? This is the ether compound with that rather long formula, C6H5OCH2CH3. Do you think this ether will succeed where the weak base completely struck out? Tracing that second arrow away from phenol, what do we find? Yup, another big, bold X. The text beautifully backs this up, stating that ethers are simply unreactive with phenol under these specific conditions. They mix, sure, but absolutely nothing happens. So candidate B is officially off the table. Which brings us to Section 4, the reactive compounds. So, we've seen 2 candidates completely fail to provoke phenol. Our concentrated nitric acid, option C, and ethanoyl chloride, option D, finally going to break this losing streak? I mean, these are traditionally much more aggressive chemicals in organic synthesis. Will they have the power to actually force phenol to react? Spoiler alert, they absolutely do. Following that third pathway, the reaction with concentrated HNO3 gives us a very clear result. We see the successful formation of this really complex product called 2,4,6 trinitrophenol. You can easily spot it by those 3 NO2 groups locked firmly onto the ring. So that confirms without a doubt that option C is a go. And if we check the bottommost pathway for our final candidate, ethanol chloride, we get another chemical transformation. The source explains that when phenol reacts with an acid chloride like this, it successfully yields a specific type of compound known as an ester. You can actually see the new functional group attached right there to the oxygen, so that's a confirmed reaction for option D too. Finally, Section 5, the final answer. Let's pull this all together. This summary checklist brilliantly illustrates everything we just discovered. We took all that dense, chaotic source material and mapped it out so we can visually lock in the knowledge. Candidate A, the rubidium bicarbonate? Nope. Candidate B, the ether? No. Candidate C, concentrated nitric acid? Yes. And candidate D, ethanoyl chloride? That's a yes.
So the main takeaway is staring right at us. Based entirely on the chemical principles from our source text, only options C and D actually react with phenol. In fact, the original text literally wraps up its explanation by stating exactly that. Only C and D react. Now, if you were tackling this in its original multiple choice test format, you'd be looking for the option that combines C and D together. And based on all our logic, the definitive answer is number 3. We just took what looked like a super chaotic chemistry diagram and completely decoded it just by following the structural logic step by step. Which leads me with a final thought for you. How is mastering these basic rules of acidity and functional groups going to change the way you approach your next chemistry exam? Once you realize that every complex problem is just a series of really simple yes or no tests, the whole subject just opens up. It's a total game changer. Thanks so much for diving into this explainer with me, and I really hope this helps you absolutely crush your next big puzzle.